Hello everyone, welcome to my channel Coding Together. My name is Vikas Oja. Today we will see and learn about the backtracking concept. So let's read a statement which will give us an idea about the definition of a backtracking algorithm. So backtracking is a general algorithm for finding all the solutions to some computational problems, notably constraint satisfaction problems, that incrementally builds possible candidates to the solution and abandons a candidate as soon as it determines that the candidate cannot possibly be completed to finally become a valid solution. So let's see an example to better understand this definition. So suppose we are given with two boys and one girl, and we have to arrange the sitting arrangement of these three students in such a way that the girl does not sit in between the two boys. So now it has become a constraint satisfaction problem, right? So every choice has to satisfy the constraint, the explicit constraint that we have defined, right? So we'll incrementally build the possible candidates to the solutions, right? So we will draw our state space tree. So what is state space tree? It's a tree with all the possible solutions for a given problem, where each solution is represented by a path from the node up to the leaf. Right. So let's try to draw the state space tree for this. So now we'll start from the start or the root node. So first, either a boy B1 can sit first, right? So this is one choice that we have made, right? Going incrementally, right? Level by level, step by step, to build the possible candidate. So we are building our candidate, right? We are going from start to B1, and then we'll choose some other thing, right, candidate, maybe a boy or a girl, and then we are building our solutions, right? So we have chosen our B1. We check our explicit constraint that girl cannot sit in between B1. So because we have placed a boy first, right? So there is only one boy, so we can go further. So now from B1 we have another choice that we can place either a girl or a boy. So let's place boy 2, right? So it's also meeting the explicit constraint that the girl is not sitting between B1 and B2, right? So we have incrementally building the possible candidates, right? So this is in this one path will give us one solution, feasible solution, or may not, that we will see. So at each level we are checking the constraint. Now we are moving to the next level where we have no choice but to take the girl, right? But it is meeting our explicit constraint. So this is our valid solution. Right? So as from girl we are out of choices, so we'll go back, right? We'll go back. Now this is our feasible solution, as I said, because this is a valid solution, right? Because it is meeting the explicit constraint, implicit constraint as well. What is implicit constraint? That the order does not matter, right? B2 can come first or B1 can come second. That is the implicit constraint, right? So it is meeting explicit and implicit constraint, so it's a feasible solution, right? Now when we go back to B1, right, because at B2 we had only one choice to make, that is girl. So we from B2 will go back to B1, but at B1 we have another choice we can make, that is placing the girl, or the girl can sit now after the boy B1 has set. So but as soon as, so we are here also, we are incrementally building our another solution, right? So we are adding candidates for the solution. We added B1 and then we added girl. So when, as soon as we found that as soon as girl sat, this is not meeting the explicit constraint, because we know that if the girl sits here, then the only choice left is B2, the boy 2, and then it will, not meet the explicit constraint. So this will not lead to a possible valid solution. So what we will do, we will remove these solution, we will remove this solution or the partial solution for, or will not consider this solution in our algorithm, and will backtrack, and will backtrack to intermediate level, that is B1, right? So this is our intermediary level, because this level, at this level we had the choices to make, right? From this level, either we can find a feasible solution or not feasible solution, right? So from a backtrack, whenever there is a non-feasible solution, we backtrack to a point where there is a way to go for another path, to choose another path that might lead to a feasible solution. And again, the choices at B1 are over, so we'll go to start, right? We'll backtrack to start, and then at start, right, we'll explore the other possible solutions, right? So we'll can say that the boy B2 can sit first, right? So we are exploring now the other solution from the start. So if the B2 sits, so at this level it's meeting our explicit constraint that the girl cannot sit in between. Now we can choose B1, right? The boy B1 can sit and the girl can sit at the last, right? So this path, right, this solution is also a feasible solution, right? So from girl, this path is also a feasible solution. So from at this leaf node, we are out of the choices, so we'll go back to B1 and B1 to B2. Then at B2 there is another choice we can take, right? That is, the girl can sit after B2. Now again, we will stop here, will not proceed further, right? We'll kill this live node, because we know it's not meeting our explicit constraint, because one boy was already set, girl is sitting in between. So the next, there will be a boy from the choices available, right? From the choices available, that is only a boy, the girl will come in between. So we'll backtrack. So we'll backtrack from here as well, and we'll backtrack to start, because B2 is out of the choices, right? B2 had two choices, either B1 and girl. So we'll backtrack to start. Now at start, we'll explore the other path to add in our possible solutions list the other solution, right? So we'll explore other path as well. So that means the girl can sit first. Now if the girl sits first, right, so we know it will lead to the possible solution, because girl is not in the middle. So it doesn't matter whether boy 1 sits first or boy 2 sits first. these two will also lead to possible solutions. So what are our valid possible solutions? 1, 2, 3, 4. So in this way we are stopping, right? We are abandoning a candidate for a possible solution as soon as we find, right, as soon as we find that the candidate cannot lead to a possible solution, right? So the same has been represented here, right? We start with a start node, we reach an intermediary level, and then if we go to a solution 1, if the solution 1 is not a feasible solution, it's not a valid solution, we backtrack and we go to intermediary level 1, right? And from intermediary level 1 to the start, then we try explore the other path with other choice, that is I2. And now I2 becomes the intermediary level, explore the other solution, that is S2. If it is not feasible, then we'll backtrack, we'll try the third option, and if it is feasible, then we'll add into the list of the feasible solutions. So let's see what problems we can solve with the backtracking. So the first is decision problem, where we have to find always a feasible solution. Now the second can be the optimization problem, right? Optimization problem, where you have to find the best feasible solution. And third is a enumeration problem, where we have to find all the solutions of a problem. Like, so for example, subset problem. So what are the examples we can go to better understand this backtracking problem? That is n queen, combination problem, combination sum, subsets, right? So these are some of the examples. We'll explore all these problems in the upcoming videos. I'll take up the lead code questions, which include the backtracking concept. We'll try to see the state space tree for each problem, right? We'll visualize the algorithm as much as possible, right? And we'll understand these backtracking concepts. So let's talk about some of the properties, I can say some of the important points of the properties of backtracking, right? So first is backtracking usually uses DFS manner. It traverses the state space tree in a DFS, depth first search manner, DFS manner, right? So that is the one property. And second, it can be called as an optimized way of brute force, right? Optimized way of brute force search, right? Because brute force explores all the possible solutions, but as we saw that backtracking like eliminates or removes or abandons the candidate for a solution as soon as it finds that it cannot lead to a feasible solution. And also whenever we are backtracking, like whenever we backtrack, we undo the last choice we made, right? We undo the last choice for this invalid solution, right? S1, whenever we backtrack, we undo the choices that we made while backing up. So it undoes the choice when it backtracks or backs up. So yeah, so thanks for watching this video. So we'll see in the future videos the more examples and more lead code problems based on this concept. So stay tuned with this backtracking series or the backtracking playlist that I will create. Thanks for watching. Please share and subscribe. It will keep me motivated to bring more such videos in front of you. Thank you guys. Bye.